Chapter 10 takes a totally different direction. 10.1 is a section on its own, then 10.2 through 10.5 that deals with Fourier and other things. And you notice so far we've been dealing with ordinary differential equations. That indicates that those are the same. Actually, let me put it that way. Since that's green, that indicates that those are the same. And do you notice here that those are not the same? That's called partial differential equations. Here, you're really looking at x being between alpha and beta. So those are on the same line, x equal t naught. Here, you're looking between two boundaries. And I need to remind you of a bit of, call it, of linear algebra, just a bit. So the first, recall that ax equal b, where a is a matrix, n by m matrix, b is an n by 1 vector, and x is what we're looking for. It is an n by 1 vector, and that's what we're trying to determine. If a is singular, then the system has no solution, an infinite amount of solutions. If a is not non-singular, then the system has a unique solution, which is b. If we set ax equals 0, x equals 0 is trivial. We're not looking for that. We're looking for a that make that happens. And when we get to chapter 7, we'll talk more about the null space and all of these awesome topics that you learned from before. Let me start with a simple problem in this section. And here it is. And it states, either solve the given boundary value problem or else show it has no solution. Problems 11 and 13 involve Euler equation. See section 5.4, not a big deal. So let me look at this. And this is a second order linear differential equation with constant coefficients. I know the drill. Let y equal e to the rt should do the trick. So I'm going to get e to the rt times r squared plus 2 equaling a 0. E to the rt, the usual, cannot equal 0. R must be plus or minus radical 2i. So I know the fundamental set is actually the cosine of radical 2x. Here we have to make the shift back to x. And the sine of radical 2x. So I know that y equal c sub 1, the cosine of radical 2x, plus c sub 2, the sine of radical 2x. So I notice I need the derivative. So I figure out what the derivative is, and that is negative c sub 1, the sine of radical 2x times radical 2, plus c sub 2 radical 2, the cosine of radical 2x. Now, if I take y prime of 0, that is 0 plus c sub 2 radical 2 times 1, and that equals a 1. So c sub 2 equal 1 over radical 2. Got it. So c sub 2 is actually 1 over radical 2. And if I take y prime of pi, that would be negative, and what did we say that was? C sub 2. If c sub 2 is 1 over radical 2, do you see that those cancel out? Y sub pi is going to equal negative c sub 1 negative, I don't know why I wrote it that way. That should be radical 2 c sub 1. Negative radical 2 c sub 1, the sine of radical 2 pi, plus the cosine of radical 2 pi. And that should equal a 0. So pretty much if I move this over to the right and divide, I'll get c sub 1 to equal is going to be positive the cosine of radical 2 pi over radical 2 the sine of radical 2 pi, and I know what that is. 1 over radical 2. Cosine over sine is actually the cotangent of radical 2 pi, and that's all there is to it. Now I'm going to say my solution is y equal c sub 1. We got c sub 1 to be 1 over radical 2 of the cotangent of radical 2 pi times the cosine of radical 2x plus 1 over radical 2 the sine of radical 2x, and that would be my final solution. So this problem is really straightforward. The numbers are not pretty, but that's fine. These things happen. If I look at number 4, and the same deal happens, this is a linear differential equation, second order. The order doesn't matter with constant coefficients. I'm going to let y equal e to the rt, and I'm going to get e to the rt times r squared plus 1 equals 0. Of course, e to the rt can never equal 0. It must be that r equal plus or minus I, and I know automatically what the solution looked like. The solution to this problem is actually y equal c sub 1 the cosine of x plus c sub 2 the sine of x. And now all what I have to do is find those coefficients, and here I'm going to notice there is a small difference between what I'm used to. This talks about y of L equals 0. So y of L is actually c sub 1 the cosine of L plus c sub 2 the sine of L, right? And if I take y prime is going to be negative c sub 1 the sine of x. I should have started backwards, right? You start with this first, but plus c sub 2 the cosine of x, and y prime of 0 is really c sub 2, and that equals a 1. So I figured that this is a 1. Very good. So here, this is a 1. Now, if I look at this derivative, I notice that this derivative gives me a 0, which means c sub 1 is actually negative sine of L over cosine of L, right? And that's going to be negative the tangent of L. So it is not as simple as me coming back and saying, hey, y equal negative tangent of L plus 1. Again, you don't have to write the 1. I'm just putting that for your notes. But since this is in the denominator, I have to take this piece one step further and say, you know what? In this case, cosine of L cannot equal 0. Where does that happen? That's when L equal pi over 2 plus pi times k, or n, where k is an integer. So here I would say this is my solution. Provided L does not equal pi over 2 plus pi k. And that would be my final answer. Number 8 is next. The same deal. This is a non-homogeneous equation. Not a problem. I know how to deal with this. I find the homogeneous first. I let y equal e to the rt, and I get e to the rt times r squared plus 4 equaling a 0. So I already know that y equal c sub 1 the cosine of 2t plus c sub 2 the sine of 2t. And since that's not part of the sine, I could go ahead and figure out the particular solution, and I could say the particular is a the sine of x plus b the cosine of x, and I need two derivatives. Y prime is a the cosine of x minus b the sine of x, and y double prime is negative a the sine of x minus b the cosine of x. And if I take y double prime plus 4 times a, that's 4a the sine of x plus 4b the cosine of x. Right? If I add those, I should get a sine of x. And here I'll get 3a sine of x plus 3b the cosine of x. And automatically I can get that 3a equal 1, which means a is 1/3, and 3b equals 0, which indicates b equals 0. So if this is 0, that's gone, that's 1/3, plus 1/3 the sine of x. That would be my general solution. Now, if I want to find C1 and C2, I would say y of 0, let me do it here since I have a lot of space, y of 0 is C sub 1 plus 0 plus 0, and that equal a 0. So in that case, C sub 1 equal a 0. That means this is no longer there. That's very good. And y of pi is going to equal C sub 2 times the sine of pi, which is 0, plus 1/3 times 0, which is a 0, and that equal a 0, which indicate 0 equals 0. That means infinite amount of solutions. If you recall, that means C sub 2 is arbitrary. It could be any value, and that will still work. So the solution will be y equal C sub 2 the sine of 2t plus 1/3 the sine of x. Oh my goodness, I'm still stuck on t. We forgive each other, right? Of course, you could write everything in terms of t, but they're going to write everything in terms of x, where C sub 2 could be any value, and that will work. And there it is. Now I'm looking at problem number 5. Same deal. I'm looking at a non-homogeneous equation. If I let y equal e to the rt, I'm going to get e to the rt times r squared plus 1 equaling 0. Well, e to the rt cannot equal 0. It has to be that r equal plus or minus I. So far, my solution is C sub 1 the cosine of x plus C sub 2 the sine of x. Now, if I look at the particular equation, it has ax plus b. I need two derivatives. So two derivatives, which is 0 plus, that would give you ax plus b, and that equals an x, which means a equal 1 and b equal 0. So plus x, that would be the general solution. Now, if I take y of 0 equal c sub 1, and that equal a 0, so this is gone. And y of pi will be 0 plus pi equaling 0. So pi does not equal to 0. We have no solution. Remember, when we're dealing with linear algebra and we're solving those equations, we have one of three cases. Either there's no solution, unique solution, or infinite amount of solutions. And that brings us to the last type of problems, which talks about, well, find the eigenvalues and eigenfunctions of the given boundary value problems. Notice this is a partial differential equation. Assume that all eigenvalues are real. Well, this is a homogeneous equation. If I let y equal e to the rt, I will get e to the rt times r squared plus lambda equals 0. So I'll get r to equal plus or minus the square root of negative lambda. Now they say let negative radical lambda equal mu. This is not necessarily I, it depends on what the value of lambda is. Let me get the first case out, and that's the simplest. First case, case 1. If I say lambda equals 0, well, if lambda equals 0, what do you notice? I know that in this case, r equals 0. That means e to the 0 times x, which indicates that y equal c sub 1 plus c sub 2x. Now, I need a derivative. If I take y prime, that would be c sub 2 equaling 0. Well, that means this is gone. And y prime of pi, well, y prime is c2 evaluated at pi, that's still 0. That gives the same value, which indicates that y, the solution, y equals c sub 1. So in this case, the eigenvalue is lambda equals 0, and the eigenvector is a 1, basically multiple of a constant. Okay, let's go for the second case. Case 2. What if lambda was, and let's go for positive or negative, let's go for negative. If lambda is negative, that indicates that r is a multiple, r is positive, right? Because it's going to be simply mu. You could leave it as radical lambda, but they like mu because of the eigenvalues and eigenvectors. Well, that indicates that r equal plus or minus radical negative lambda, or r equal plus or minus mu, but mu in this case happened to be positive, so that's e to the ux and e to the negative mu x, and that would mean that y equal c sub 1 e to the mu x plus c sub 2 e to the negative mu sub x, and the same deal. Now I want to find the derivative. Well, y prime is going to be mu c sub 1 e to the mu x minus mu c sub 2 e to the negative mu x. And if I take y prime of 0, the first case, I will get mu c sub 1 minus mu c sub 2 equals, oops, I said it but I didn't write it, and y prime of pi is going to be mu c sub 1 e to the mu pi minus mu c sub 2 e to the negative mu pi. And in this case, if I really want to solve one in terms of the other, you could do that. You could say the top equation says c sub 1 equals c sub 2, right? If you move this to the other side, divide by mu, which indicates in the second equation that, oh, and this equals 0, by the way, it's right there. This indicates that mu c sub 1 e to the mu pi minus mu c sub 1 e to the negative mu pi equal to 0. If you factor c sub 1 out, that is mu e to the mu pi minus mu e to the negative mu pi equaling 0. If you divide both sides by this constant, you will get that c sub 1 equals 0. That indicates that both of these are 0. Well, if both of those are equal to 0, that would mean this is the trivial case. Alright, And let me deal with the third case. Let's say in this case, case 3, lambda is positive. Well, if lambda is positive, that indicates that r equal plus or minus mu, and there's an I because this would be, oh, I don't write it there. The I will come out of the negative because that's a positive. And in this case, what I'm really looking for is y equal c sub 1 the cosine of mu x plus c sub 2 the sine of mu x. And now the same deal. If I take y prime, that's going to be negative mu c sub 1 the sine of mu x plus mu c sub 2 the cosine of mu x. And if I go back and use the first case, y prime of 0 is going to simply be mu times c sub 2, and that equals 0. That means c sub 2 equals 0. This term is gone. And if I take y prime, so if c2 is 0, this is gone. And if I take y prime of pi, that would be negative mu c sub 1 the sine of mu pi, and that equals to 0 as well. Well, out of this, if you say c sub 1 equal to 0, that's the trivial case. Or, if you say the sine of mu pi equal to 0, where does that happen? That happens when mu x and mu pi equal to 0 plus pi k. Well, doesn't that mean mu equal just k? Wouldn't that be all the solutions? So here, if I really wanted to match what I did up there, we are going to say the eigenvalue is going to be lambda sub k equals, and remember how lambda works? Let's go back. Remember here, we set this equal to this. Doesn't that mean if you square both sides, you get lambda equal mu squared? So in this case, lambda is going to equal mu squared, which is k squared, and the eigenfunction is going to be y sub k equaling, I need to shift this just a bit to the left. Here, let me just, otherwise it's going to run out of sync. Here we go. And y sub k is going to equal cosine of mu, and we know that mu is kx. Now you could put c sub 1, it doesn't really matter, right? The reason they wrote 1 here instead of c, in case you're wondering, that's when you said back in the days when you had like x equal c sub 1 2 c sub 2 as a vector, and you took c sub 2 out, 1 2, and you said the span is actually any multiple of 1 2 back in linear algebra. That's kind of what it is. So any multiple of that will do, right? And there's our homework.